Our next speaker has studied in Bielefeld, and he studied... What he did is he studied laser physics, and now he's working at the Max Planck Institute for Extraterrestrial Physics. And today he will explain you how it is possible to use laser light to enhance distorted images that were taken from the Earth of stars and galaxies and nebulas. So I want to hear a really loud and warm applause for Peter Buschkamp with Shooting Lasers into Space for Science.
All right. All right, thank you for the nice introduction. Thank you for coming here this evening. I'm very excited to speak at the conference. Finally, I find a talk where I can contribute after all those years. I'm not going to talk about Bielefeld. You might want to hear something about that. I'm not allowed to tell you, right? Okay, so today I'm going to talk about a bit what is in my field of expertise. If there's one thing I want to bring across to you, then it's not about a single person showing this to you this evening. This is a team effort, and a real team effort. So most of the images are done by a colleague of mine, Julian Ziegeleder, and the PI of the project, so the leader of the project, Sebastian Rabin, has contributed some slides. And I wouldn't be standing here today and showing you these images if it wasn't for a huge team and many people. And I hope this is reasonably complete, but I think there were even more. Many people have tributed most and long years of their career into such a project. So this is never about something which a single person does and he or she finds something very cool and then saves the world. No, it's always a big, big team. But before we actually see the lasers then in working, we have, of course, to clarify why we do this. This is not just because we can, but there is a reason for that, because if you want to get funding, you have to write a reason, and a reasonable reason, not just because we want to. So in the first part, I will introduce you to the whole thing, and we'll talk about a bit about the problem which we want to tackle with this kind of technique. I will mostly present only diagrams, not actual hardware blocks already, so that you get the basic concept. So when we do astronomy, we do two types of things. We either do imaging, which is we maybe produce a nice image of a star, so that's a blob over there, or we take this image, maybe this little blob over there, and make it into a spectrum. So we disperse the light, and then we look at the differential intensity between the diverse colors, or other maybe, for example, you see black lines in their absorption bands, and so on. To do such a thing, you need a spectrograph, and in a spectrograph there's a thing called an entrance slit. So in this slit you have to put over your objects so that you don't get light from left or right next to the object to what you want to observe or analyze, so that you only get light from where you want it. The thing is now, this slit cannot be made arbitrarily wide or small, because the width of the slit directly determines what kind of resolution you have in such a spectrometer, as it's called. This is a quantity which needs to be above a certain value when you want to do certain kinds of analysis. So it has a fixed width. So now if we look at an image produced of one of the most capable telescopes on this planet, and we put a representation for the slit over the star, okay, now it's white, let's make this black, then you see if you want to go for that star over there, you do have a problem already. As said, you can't make the slit wider, but the star is actually larger than the slit, meaning that you lose light. Well, then you lose some light. No. If you want to do quantitative measurements, you want to have all the lights and all the pixels. So you can't get rid of them and just throwing something away. But our image is looking like that. It's maybe nice, but can we do better? Yes, we can. And this is what we can achieve with adaptive optics. This is an image that has been produced with adaptive optics with a laser AO-assisted system. And if I flip back and forth, you see there is a difference. All right. So, why is that? Why don't we get these ideal images? The reason is because there is the atmosphere. The atmosphere is great for breathing. It's not that great for astronomy. So if you have a star up there somewhere in outer space, it can be very far away, so the photons might have traveled for 11 billion years, and now they finally hit the atmosphere, and then something happens which you do not want. Okay, first they travel freely. There's a nice planar wavefront, so it's not disturbed by anything, maybe something, but that's not the scope of this evening. It's planar, it's nice. And if you actually have a satellite, it's very cool, because then you can directly record this undisturbed light. If you have something on the ground, well, you do get a problem, because the atmosphere introduces turbulence, because, well, the air wobbles a bit, there are streams coming from all directions, there are temperature gradients in there, and these all work together and make from this nice planar wavefront a crumbled one. If you have a perfect image which you create, this is called diffraction limit. This is just limited by the size of your optics. So the wider your optics is, the nicer the resolution is of your image. If you then build a large facility with maybe 2 8-meter mirrors on the ground, well, you only get a seeing limited image. Seeing limited, the seeing is this wobbling of the atmosphere, as it's called. And that's about it. You can make it arbitrarily large. You won't get a better resolution than a backyard telescope of having 20 centimeters in diameter. So, yeah. What to do? There have been people, of course, thinking about this problem longer. And the first idea came up in 1953. And some guy at Palomar Observatory in California said, well, if we had the means of continually measuring the deviation of rays from all parts of the mirror and amplifying and feedback this information so as to correct locally the figure of the mirror in response to the Schlieren pattern, we could expect to compensate both for the seeing and for the inherent imperfection in the optical figure. What? So if we could somehow get rid of this wobbling or counteract that, then we could get this perfect diffraction-limited imaging we get in space also on the ground. In the 1970s, the US military started to experiment on that. Well, I guess the Russians too, but it's not, yeah, it's known that the US started at Starfire Optical Range. In 1982, they built the first AO system, adaptive optics system, the compensated imaging system on Hawaii, and in the late 80s, the first astronomical use adaptive optics systems, come on, as it was called, installed at the Observatoire Haute-Provence and at ESO in La Silla, that's the European Space Observatory. All right, so that was, we get from this fuzzy blob. Actually, we found that this fuzzy blob is not a fuzzy blob, but 2 fuzzy blobs. Well, it's a binary system, as I would say it if this was, at an astronomical conference. But yeah, you disentangle things you could not see before. Okay, how does this AO system look like in principle? So again, we have the stars somewhere. We have learned already that we do have, actually you see this slight Schlieren pattern in the air from the warm and the exhaust from the, yes, there's a bit of flimmering in the background, and that's seeing. Okay, so the image is not as sharp here as it comes from the projector there. Okay, that comes from somewhere, and then we need a system which has 3 components. One is a deformable mirror, the other is a wavefront sensor, and the third one is a real-time computer. We need something to actually measure what is going on, then we need to take this measurement and extract some information from this measurement. And then we need something which can correct this wavefront, straighten it out, so to speak, because we want to have it straight again. So the wavefront sensor sends some information to the real-time computer. This some information, namely, is what is the curvature? How does this wiggled thingy look like, the wavefront? And that real-time computer computes then information that goes to the deformable mirror, and that is in real-time shaped to an arbitrary shape, counteracting that incoming wavefront, and then straightening it out. So we do have a light path like this first, so it goes on this deformable mirror, goes on something else, which I will come to in a minute, and then on this wavefront sensor. And of course, that means if you run it, you do have a control loop. Meaning you measure something here at the wavefront, you put the information into there, feeding that into the deformable mirror. That deforms somehow, modifies this wavefront that comes from above. And then, of course, you want to have a feedback loop. Is that what I did enough? Do I have to do more? And also, of course, the next in the next second or split second, this pattern will have changed because the atmosphere is dynamic. If it wasn't dynamic, we don't need to do this in real time, but we have to do it in real time. Real time meaning we have to do this correction and calculation and sensing at a rate of about 1 kilohertz, so 1,000 times a second. Then we have a scientific instrument because actually we do want to see what is in there. And so this thing in the middle is a beam splitter. It takes some of the light, puts it to the wavefront sensor, not all, because most of it shall go into the scientific instrument. And there, as you see here, then the wavefront is straightened out again, and then I can focus it into my instrument. To do actually that, I have to do, this is the one slide in this talk with a Greek symbol. You have this incoming wavefront, which is shown in orange, and then you do a piecewise linear fit, which is an approximation of the slope of it, actually how it looks like. It's put into linear pieces, and this the size of what is normally can be taken as a linear fit piece is roughly 10 to 15 centimeters for good observation sites, while this thing here, so this is the primary mirror of the telescope, which collects all the light that comes from outer space, is usually, for the big telescopes, at this point, 8 to 10 meters. Okay, but how do we get this slope? Now we know that we can approximate it in pieces, but how do we get the slope? Because we need these slopes, of course, fed into this deformable mirror to maybe, okay, if it comes like this, I go like this, and it comes in nicely, or comes out nicely. So in this way, a sensor comes in. There are different types of these sensors, but the one we are using is a so-called Shek-Hartman sensor, and it looks like this. This is the ideal case, of course. So we have an incoming planar wavefront, straight on. Then we do have an array of lenses. So it's just 1, 2, 3, 4 lenses, and then in an array, like 4 by 4. And they all focus what is coming in onto a detector. And if this wavefront that is coming in is planar, like this on the left, then you do get a regular spaced grid of focus points. In this case, 4 times 4, so 16. If now the incoming wavefront is not planar, it looks like this. So the focus points do move a bit because, well, it came maybe like this, so the focus is offset. I will flip it back and forth again, so it's looking like this. And you see, of course, you do know what is perfect, meaning they are at their designated grid points. If it's imperfect, well, then just measure the deviation from their zero position, so to speak, and then you do have a proxy for this slope. Of course, it's a bit more complicated than that. There are matrices involved, which are not necessarily quadratic. and you have to invert them, and if you don't, yeah, no. They're pretty clever people and programmers working on these type of problems, and this is actual current research. This is far from done, this field. Okay, so suppose we do have the slopes, then we take a deformable mirror, and this is the zeroth order approximation of a deformable mirror. Let's say your wavefront looks like that. Well, then take just a mirror which is maybe recessed a bit in the middle, the other type forward. It bounces on this mirror, and because there is something sticking out there and in there, well, that approaches there, goes back, and in the end, the whole thing, when it has been reflected, is planar again. Okay. That is, well, as said, the easiest order approximation for that. It's a bit more complicated. Your incoming wavefront doesn't look like that. It's normally a bit more complex. And that means you do have to have more wobbling in your deformable mirror. You could do this. That's in the upper diagram. You could do this with a membrane, which is continuous, or maybe it's also in pieces. And these segments are driven up and down, or maybe tilted by piezo stages that are put underneath. Remember, they have to do this like 1,000 times a second. Or you could do something like you take 2 piezoelectric wafers. They have opposite polarization, put electrodes in between, and then when you apply a voltage to these blue electrodes, then you have local bending. So the one thing will bend up, the otherwise will bend in the opposite direction, and then you do have changing curvature on this whole thing. It's not that easy, of course, in reality, because they are not completely independent. One cell will influence the other, and yes. But this is the basic principle. Okay, now you have seen there was this beam splitter. So most of the thing goes into the science instrument, and some goes to our wavefront sensor of the light. If the object we want to record, like a galaxy that is 11 billion light years away, then this galaxy is too faint. We can't analyze its light. So what do? We need maybe a star that is nearby. So our galaxy, which we actually do want to observe, is the red thingy. The bright star is the yellow one. And if they are reasonably close together, reasonably close meaning about 10 to 20 arc seconds. If you stretch your arm and look at your little finger at the fingernail, this is about 30 arc minutes. 1 arc minute has 60 arc seconds, so it's very close. It's not the galaxy is there and the star is there. No, it's there. Because if you have a large separation, then they do sense different turbulence. Simple as that. Now the thing is that less than 10% of the objects you have on the sky, which you're normally interested, do have a sufficiently close and bright star nearby. So what to do? And now we come to the lasers. Because if you don't have your, well, if they don't want to play nicely, well, build your own theme park with, yes, you know. So, make your own star. This is what we do. Because if the star is not nearby, a sufficiently bright one, well, why has it to be sufficiently bright? Because if you want to do this computation 1,000 times a second, well, then the time you can, the time for your CCD, where you record this image from the wavefront, well, it's a thousandth of a second. And if you don't have enough photons in a thousandth of a second, well, then there is no computation of this offset of these little green dots on their grid. So you need a lot of photons. So let's get enough photons. And there are actually 2 things what you can do. There is a conveniently placed sodium layer in the upper atmosphere. It's 90 kilometers above ground, and there's a sodium layer. And what you actually can do is you can take a laser on ground here, and then shoot a laser which corresponds to the energy transition of these sodium atoms. which is 589.2 nanometers. It's orange. And excite those atoms up there in the atmosphere, and they will start to glow. And if you have a focus, if you focus it in there, and then you have a blob of sodium atoms lighting up in the upper atmosphere, maybe whatever, some 100 meters long and some meters wide, as big as your focus is there. This can be done with a continuous laser. This has been done in the past, yes, of course. And actually the first instruments were built like that. The thing is, in those days, they were very, very expensive. There is no sodium laser. There are only dye lasers, and they are messy and expensive. Nowadays, we can build this as fiber lasers, but not 10 years ago or 15 years ago. Another solution is to actually use the Rayleigh scattering in the atmosphere. You use a neodymium YAG laser, which is 532 nanometers, is green. It's easily available. It's cheap compared to the other one. And then you focus it in the atmosphere. The only thing is you will have backscatter of photons all along the way. So you have to think about how can I only record light from a certain height above ground? Because otherwise I don't have a spot because I have a laser beam column somewhere there. Okay, how do these things look like? Can we dim these lights actually a bit? Or is it only an off switch? Can you check on this thing? Yeah, let's check on that. Just push the button. Come on. No. 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 It's still on here. All right. It's looking like this. Who has been at the camp? There was an astronomy talk at the camp from Liz. Okay. Actually, if this talk had been tomorrow, we would have had a live conference to that size because Liz is right now here. And she sent me that picture just some hours ago. That's how they just do things on Paranal in Chile. The thing I will talk about is the green one to the right. That's the thing I have been involved with. Yeah, let's look into that. So if you shoot the laser into the atmosphere, of course, you do have a problem. The star is very far away, is infinitely far away, and the light that comes down is in a cylinder. And if you shoot a laser up, it's a cone. So you only probe the green region, and the unsampled volume of turbulence is to the side. That is a problem with our laser AO. Another problem we face is this one. When we take a star to measure the wavefront, then it passes only once through the atmosphere. The laser beam goes up and down. And so there is a component called tip-tilt component, which is actually just the thing moving around. It's not just this, the phase that gets disturbance that gets introduced in the wavefront, but this moving around. Not the bright and more or less bright twinkling little star thingy, but the moving around. And that can not be sensed with a laser guide star. So whenever we do laser AO, we do need another star to get this component. But this star can be a bit further away, like an arc minute or 2 arc minutes or so. So it's that is why. There are enough. And then we should think about actually what we have to correct. And so we should make a profile of the turbulence above ground. And this is how it looks like. And for example, for the site where we are there in Arizona, we see that most of the turbulence is actually just above the ground. So we maybe should care mostly above the ground layer. It's not so much about the high altitude things. So, and then what we do is, well, we want to sample the ground stuff nicely. So we just don't take 1, but 3 lasers. So to fill this area nicely. And yes, of course, we can also combine this, and it looks like that. This combination we will not talk about today. We will only talk about that. This is how it looks like. So this is our telescope, the primary mirror, which receives the light from outer space. It then deflects on the secondary, tertiary, and then somewhere here. But first, we need to have to shoot the laser up, and it's launched from a laser box onto a mirror behind that secondary mirror over there into the atmosphere. And after 40 microseconds, it reaches an altitude of 12 kilometers. And of course, it comes back. After 80 microseconds, it's here in our detector again. So the star then lights up, has this cone, gets focused there, focused, reflected to here. And we do have our signal in our detector after 80 microseconds. And as said, because of course the laser has scattering all along its path, you want to gate this information to 12 kilometers. And well, then you just look at when your laser pulse started. Wait. Open the shutter for the detector for a short time. After 80 microseconds, close it again, and then analyze and read out what you just did. Easy, huh? So we're done. Thank you for coming to my talk, and now go out and build your own lasers with two. Now we're going to look at this thing which is actually built and which works. So this is called Argos. It's a ground layer AO system. That's what we want to build. It has wide field correction. That means you cannot correct just a tiny patch on sky, but for astronomical use, a huge area, meaning it's not just a circle of 10 arc seconds, but this thing can correct 4 by 4 arc minutes, which is huge. So all the objects that are in there. We have a multi-laser constellation. We have seen that. Why we need this? Because we want to fill the complete ground layer. So we have 3 laser guide stars per eye. Why per eye? This will be clear in a minute. And we use high power pulsed green lasers. And this deformable mirror is actually built in the telescope system already. The secondary mirror is the deformable mirror, which is very convenient because then all the instruments that sit on the telescope can benefit from this system. It's installed at this telescope. Looks pretty odd, yes, I admit that. That's the Large Binocular Telescope. It's 2 telescopes on one mount, 1 primary, 2 primaries. It's roughly 23 by 25 by 12 meters. It sits on Mount Graham in Arizona. And it has an adaptive secondary mirror, which is this violet color thingy up there in the middle, on top. This is how it looks like. This is the control room where you sit. This stays fixed. All this shiny part rotates. That's the actual telescope, the red thing that moves up and down. So the whole building rotates and moves up and down. It's from the ceiling as is at level 11. So when you actually sit there, you can watch around a bit. So okay, that's outside. It's winter. Ooh. Okay, let's see. And there's a ladder. Okay. Yes, this thing is huge. Yes. Okay. Nice. Cool. Okay. That's how it's looked like when you're actually there. Okay. Our system layout is like this. We have this adaptive secondary mirror, which is the deformable mirror. We have the primary, tertiary. That is clear already. So we have a laser box. The green thingies being the lasers themselves. So that's how it looks like. We produce some laser beams. We have steering mirrors in there to get them into the right pattern on sky, of course. We do have control cameras. If is the focus right, is the position right. This is a control loop, another control loop, another control loop, and another control loop. The black thing is the shutter, because we have to close this whole thing when aircrafts are overhead, when satellites are overhead. So if you want to use this system, you have to put 6 weeks in advance. You have to put out your list of observable targets to some military agency, and they will tell you, okay, not okay, okay, not okay, not okay, not okay, okay. Not okay meaning something is passing overhead. What could this be? Of course, at some point, the lasers come down again in this cone shape. They will reach the primary mirror. And ultimately, it will end up in the wavefront sensor, which is much more complex than just this box I showed you before. So there are acquisition cameras which detect, are we at the right spot? Do the spots get onto the detector in a nice fashion? We do have to do this gating, remember? We have to open this shutter for the CCD when we want to record the light for this tiny fraction after 80 microseconds, after the laser pulse has been launched. That's done in here. These are Pockels cells, so it's an electro-optical effect. And then there's also something in addition, because, well, I said we can't do without the tip tilt. And there's another unit in here that sits right in front of the science instrument that detects this tip tilt star, this additional star. And so you have the laser wavefront light, the green one. You do have this tip tilt light, the blue one. And you do have the actual science light from the object you want to observe on sky that goes directly into the scientific instrument in the end. And then you have a lot of control things. Of course, you do need a common clock for this synchronization of all these pulses and the gating and whatnot. And of course, you need the information for the tip-tilt component and for the wavefront into this computer, which sends then all the slopes. You remember, we have to do this linear approximation piecewise, yes? Into the secondary mirror, which then deforms in real time and does this 1,000 times a second. This is how it looks like. So when I'm there, I'm roughly that tall. The two black tubes right in the middle, those are the two tubes which go up. Looks like this. So this is how the components are distributed over the telescope. Once back, okay. Primary mirror, some instruments in the middle, some tertiary mirror, the secondaries, the adaptive ones up there. Yes, I hate to use these laser pointers. No. Because I'm always going like this. It's my man. So, okay. So we do have the adaptive secondary up there, and then it goes back on the tertiary down there, and then goes over into the science instrument or the wavefront sensors and whatnot. Again, we do have a laser system. We have to place somewhere a launch system for the laser, a dichroic to separate between the laser light, the tip-tilt light, and the science light. We do have to have a wavefront sensor to check how the wavefront looks like. We do have to have this tip-tilt control. We have a calibration source would be nice to calibrate the system during daytime. Aircraft detection, yes. Satellite avoidance, also an issue here. And a control software. There are many people just writing software for this, and this is really hard. Some are also on this conference. They don't want to be pointed out, as I learned, but you will find them at the conference if you look at the right places. That's where the laser box is located. Just next to it is the electronics rack. How does this thing look like? So that is one of our lasers. It's about 20 watts. Don't get your finger in there. It really hurts. And if you know, there's a mandatory annual laser training, of course. Yes. And if you want to have something like this at home, you do need a huge refrigerator next to it just for the cooling of that thing. This is nothing you want to have at home. Just because it's that bulky, it's nothing. No, it's not. Because actually, when you do this green laser pointer thingy, then there's always this, don't use it for more than 10 seconds. Because why? Because the crystal inside heats up. And if you can't dissipate that heat, the crystal at some point breaks. And then your laser pointer is broken. This thing gets continuously cooled. So therefore, it's a bit more expensive. If you then put it up, so this is still on the lab table when it was integrated and tested, and then at some point it gets put all in a box with all these control mirrors and cameras and whatnot. But finally, you see in the middle on this picture, there is a focusing lens, and then you see these 3 tiny little beams coming out of there, which then expand on sky, well, like in that size, of course, if they're in 12 kilometers height, but that's how they come out of it. And if you install this in the telescope, you actually have to tilt the telescope, because otherwise you can't reach it, and then you need your climbing gear. So once you have produced the lasers, you need to propagate them through a dust tube onto a launch mirror, a folding mirror, and from there to a launch mirror. Yes, and then it looks like this. Okay, so the lasers come from here into that, and then over to the other side, over the secondary mirror, and then being shot right up into space, like this. Okay, so if you want to have that at home, yeah. But I can tell you, the whole facility does cost less than one fully equipped Eurofighter. Okay, thank you for taking the hint. Yeah, that's how it looks like. It's yeah. Okay, I have to admit, these are a bit longer exposures. It's not that bright and green when you are actually at the telescope up there, but if you have been in the dark long enough, around 10 minutes, then it really becomes bright. There's a little telescope that observes where actually the spots are on sky, and if we have clear sky, then we have this constellation on the right, so that is how the lasers come up. As said, you do see them all up the way up, but we are interested in the little dots at the end. You can barely see them. If there are high clouds, well, then we produce something like this. We have the dichroic when the light comes back down, as said, which separates the science light in red and the laser light in green. This is how it looks like. Actually, the dichroic is right in front of Sebastian there. And from there, it gets then reflected on a reflector and then up into the wavefront sensing unit. So there is the dichroic, there is the reflector, and then it goes over in this unit, which is the wavefront sensing unit, which sits there at the side. That's how it looks when it gets installed. And that's how it looks inside. So you have the 3 laser beams coming from the side, from the sky, of course. You have patrol cameras which monitor where are these. Are they at the right spot? Do we have to steer the lasers a bit? Then we have some control for the position of the laser spots and the field. The Pockels cells are the ones that do this opening and closing in front of the shutter. You can't use a mechanical shutter in front of the CCD. You have to do this electro-optically. So you have a polarization of the laser beams, and you have a polarizer, a cross polarizer, and then you just turn the polarization of the crystals. It's an electro-optical effect, and then it gets passed through or it gets blocked. Then you also, of course, have the lenslet arrays in there, and then the CCD, which actually records this dot pattern. You remember this 4x4? Well, it's not 4x4. In our case, we do have a bit more resolution. The sensor reads looks like this. This is actually a custom-built CCD, very special. The imaging area is in the middle, and when you read out the thing, you split the image in half, you transfer it to the sides, to the frame store area, and then read it out. Because readout is slow, transfer is fast, and you have to do this 1,000 times a second. At very low readout noise, which is only 4 electron readout noise. For the experts here in the audience, this is very good. It's not many pixels, but it's more than enough for us. So how does this look like? It looks like that. So there you have your pattern again, your regularly spaced pattern. Of course, from 3 laser guide stars, you get 3 patterns. And then you analyze, well, the position, the relative position, the absolute position of those dots on their grid, and somehow compute the slopes from there, feed them back into, compute them actually electrical information from them, which you can then feed into your deformable mirror again, which sits on top of the telescope. And then hopefully everything works. This you can digest at home. It's in the stream now, so it will be saved for all eternity, and all the aliens which record the electromagnetic field from Bielefeld. Ooh. Anyway, so just in short, there is down in green, there is this thing that goes up from the lasers to through some steering mirrors. We have diagnostics, and we go to a focus check, a launch mirror 1 and launch mirror 2 onto sky, and then we go back up there. M1 is the primary mirror, and then we go through this whole chain, and there are various control loops sitting in there, and all these things have to talk together on very high rates. Sometimes you see 1 kilohertz, other things are a bit slower, but this all needs highly sophisticated control software. And the programmers can be real proud of what they did in the past with all these control loops. The tip tilt is much easier because, well, you remember this tip tilt, so just the moving around. So you have 4 quadrants at a little cell, and if it moves to somewhere up, down, left, right, you can easily detect that, and that is fed into a array of 4 avalanche photodiodes to actually record this. And for that, we don't need many photons, so this tip tilt star can comparably be comparably dim. The calibration unit for daytime calibration can be put into the beam, so these arms can swing over the primary mirror, and then we can inject artificial stars via a hologram into the whole unit during daytime and calibrate this whole thing. And then, yes, we are back here. This is how we look like. And yeah, maybe concentrate on these 2 areas first. I will flip back and forth many times. But yeah, what is this? Are these 2 stars which are just fuzzy and dim? Or is this an extended object? The upper one may be a galaxy because it's elongated. Okay, concentrate on that. Oh, it's actually just a bunch of stars. And this is over a huge field, so the correction is not just in the middle, but you can see also at the very edges of this image, we do see this improvement in image quality. Of course, you can have the diagram if you want. So the blue line is without the thing being activated, open loop, and if we close the control loop to do this measurement and correction in real time, we do squeeze all the energy into very few pixels, which of course also mean our signal to noise level in a single pixel goes up tremendously, meaning you can decrease your exposure time, which is important. If you want to observe galaxies at these telescopes, it's $200 a minute. It's not cheap. Okay, good. So the thing, just last week, there was another commissioning run for this system. And my colleagues, José Borrelli and Lorenzo Busoni, have done a nice video. The music, by the way, hello gamer, it's royalty free. So if it was now darker, therefore I asked, this would come up nicer, but let's see. There is sound, hopefully. So the sound guys, let's see. Yeah. Of course, this is a longer exposure. It's not that Star Wars-like. I would have loved to use some Star Wars tunes along that, but yeah, you know, all these rides and whatnot. Yes, anyway. That's how it looks like. So you have 3 laser beams per eye, per telescope. Remember, we have 2 telescopes on one mount. They look roughly in the same direction, but still. So if you observe 2 telescopes at the same time, it's only $100 a minute. This is, well, not so much the shiny part on the dome itself, but if you actually do stand on the mountain during night and are a bit dark adapted, you see the laser beams like that. And don't be fooled. If you are at the valley or very far away, you hardly see them. You don't see them at all. You see them there. If you are 2 kilometers off-site already, it's merely a dim greenish something. If you are down in the valley 10 kilometers off, you don't see them anymore. If you take a camera, 5-minute exposure, yes, but otherwise, no. There is no such thing as the people in the valley down can see like these laser pew-pew every night, and no. No, nothing. Okay, which gets me to the last part. How do you become and how do you work as a laser rocket scientist? Yes, I put this in the talk directly because I do get this question in the Q&A normally when I talk about these things. And it's always like, well, what do I need to do if I want to do this? And maybe you have already an idea about this because you have seen how complex this thing is. And there are so many things to do in these kind of projects and on various levels, also in administration, also being senior people, new people, maybe master thesis works on that, or bachelor, or PhD, or then as a postdoc. It's very complex. Yes, and it's not only about just shooting the lasers in the end. Sometimes it's just checking the cables. Yeah, but it needs to be done. There is a tremendous amount of electronics and electrics involved. There are all the mechanical components in such a system are custom built. Either the institutes build it themselves, or they give it out of house. There are these real-time computers, for example. This is, by the way, our real-time computer from Micrograde. If you want to look that up, it's a company who builds these things. They need to be programmed. And, actually, if somebody is here in the audience with really hardcore experience on real-time computing, coding, on such thingies, do talk to me. This is how our software system looks like. A very small part of the GUIs. It's a lot of code and a lot of work and a lot of sleepless nights in front of these computers and just testing it and then testing some more and testing even more. And so to be involved in these kind of projects, you don't need to be a laser physicist because there is no one thing. If you want to take 3 messages out of this, it's a team effort. There are many tasks and there are many jobs, and you have to pick one. Because in this one job you do in these projects, you have to be very, very, very good. Because there are other people that are very, very, very good. If you work in these kind of projects, if you meet a new person for the first time, just assume that he or she knows everything about this and you know nothing. You will quickly realize if that is true, but otherwise, if you assume it the other way around, you just make a fool of yourself, okay? Don't do that. People in science, second most important thing, if you really want to go into this, people in science are just like people outside science. Meaning you will meet nice people and you will meet just like in life. It's not that these things are spheres where people are, you know, floating above the lab surface in nice colored. No, it's hard work. And if you actually go into this, like study physics, or maybe if you want to construct these, of course, all the drawings are done by people who have learned this in their studies. So Maschinenbau, whatever. Go for that one. Building optics needs optics experience. If you want to actually build stuff, well, there are many people in these institutes or universities who work in the mechanical fabrication departments or electronics departments. They just do PCB layouting all the time, but these things do need sophisticated electronics, and this is all custom built. This is nothing you can buy off the shelf, nothing of it, almost nothing. And this means you might end up at something equally cool. It's not that you can have this one thing and then, bam, 10 years later you will be the laser rocket scientist. You won't. You might become one, and then even after 10 years you might realize this is not the thing you want to do forever. So I have to correct the introduction in one point. I'm no longer working there. I recently left. I now have my own company. I'm still involved in these things. I do calculation for these kinds of things, but I'm not at an institute anymore. Because I decided, for example, for me, that the contract conditions in this type of scientific work are not of the type which I want to live with anymore, like one-year contracts. And so there are many ways of being involved in this. And don't just focus on this. Focus on what you really want to do, and you might end up in this. And if you don't, well, you do something equally cool. Right. Questions?
Okay. First of all, thank you for our daily dose of lasers. I have kind of sad news because we have really not much time left to Q&A. So I'm first asking the Signal Angel if there are any questions from the internet, because was that a 2? 2, okay. Because
right.
These people can't ask questions afterwards. So
yeah, I'll be all Congress, and if you want to reach me directly, 7319 is this telephone.
Okay, so the Signal Angel questions.
Yeah, the first question from the internet was how strong the laser actually is, or it could be any danger for something in the vicinity.
Actually, no. So we shoot up around 15 to 20 watts per laser beam. If there was actually a plane flying through our laser beam, then nothing happens to the pilots. They don't get blinded or whatnot because it's the beam size at that altitude is so big already. They will, of course, go like, "Ook, what is this?" And that's not what we don't want because then they might push some other buttons which they're not supposed to push. If you, of course, work directly at the system, you have to maintain it, you open it, you have to align the lasers and whatnot. Beyond their self-aligning capabilities, you do have to wear all these protective laser goggles and whatnot, because if you don't, you do have instant eye damage. It's not that, no, it's instant. You might not see it instantly, but the instant, it's there instantly, period. So really, folks, don't experiment on this laser stuff at home if you are not following basic laser safety rules. Not prying these things from the DVD burners and whatnot, Blu-ray thingies. Does it really work? just don't. Your eyesight is not worth it, period. It's not.
Please remember to cover your still working eye.
Yeah. Only look into the laser beam with your remaining eye.
The other question?
And the second question from the internet was, it was actually commenting that it's a very cool concept already in use, and where do you see this going in the next 10 years? So what's the outlook for observation from the Earth's surface in the next 10 years?
Oh, of course, the telescope will get bigger and bigger. The next generation of telescope is coming up in the 2020s. The European Extremely Large Telescope will be roughly around 40 meters in diameter. These are so huge, they can't work in seeing limited operation anymore. They do have to have laser AO all the time. It will look similar to this. So this is, in this sense, also a technology demonstrator. There will be a combined thing. You remember this diagram with the one sodium laser in the middle and the others outside, so these combined things. And then you can also imagine something that you probe different heights in the atmosphere, because you do have different turbulence layers. And all of these then have their own deformable mirror. So it gets a very complex setup, multi-conjugate AO as it's called. And then there are, of course, there's research being done on how to detect this wavefront most efficiently. And there's a so-called thing called the pyramid sensor. You can look for that also. We do have one in our system. And this is very efficient. So it takes much less photons to get to the same signal-to-noise level. This is active research, and well, every major telescope, of course, now has this, and every big telescopes in the future will have this all over the place.
Okay, we're completely out of time again. So again, thank you very much.
Thank you.